All right, let's talk about a fundamental concept that, believe it or not, powers a huge chunk of our digital world, usually right under our noses. We're talking about sets.
Okay, let's just dive right in with a little thought experiment. Imagine you need to make a list, say a guest list for a party, but you have two very important rules. First, no duplicates are allowed. You can't invite the same person twice, right? And second, the order doesn't matter at all. Whether you write down Alice then Bob or Bob then Alice, it's the exact same list of guests. So, what kind of data structure could possibly handle that?
Well, the answer to that little puzzle is a tool that's both surprisingly simple and incredibly powerful. So let's pull back the curtain and meet the star of our show.
And here it is, a set. Now, you see this fancy term here, abstract data type, or ADT. Don't let that scare you. All that really means is it's a blueprint, a set of rules for storing stuff. And for a set, the two most important rules, the ones that define its entire existence, are right there, unordered and distinct. These two words are everything. Let's break them down.
So first up, unordered. This one's easy. It just means the sequence you put things into a set makes zero difference. A set containing the numbers 3, 7, and 9 is exactly 100% the same as a set with 9, 3, and 7. The only thing that matters is what's inside, not how it's arranged. This is super efficient when all you need to do is ask, hey, is this thing in my collection? You don't care where it is, just that it's there.
And then there's the distinct rule. This is the one that prevents duplicates. So let's walk through it. We start with an empty set, and we add 67, 91, and 14. Cool, no problem. Our set now has those three numbers. But watch what happens when we try to add 91 a second time. Nothing. Absolutely nothing happens. The set sees it already has a 91 and just, well, ignores the request. Simple as that. One of each. That's the rule.
All right, so now we get what a set is. It's this special kind of collection where order doesn't matter and everything is unique. So, what can we actually do with one? Let's check out the basic toolkit. Pretty much every set you'll encounter comes with these fundamental operations. You can add a new element, you can remove an element, and you can ask for its getLength to see how many things are inside. And that total count, by the way, has a cool-sounding name you might hear sometimes. It's cardinality. So let's see how these rules work together. Let's say we just start throwing numbers into an empty set. We add 91, then 74, then 86, and then we try to add 74 and 91 times again. What do you think happens? The set just acts like a bouncer at a club. It checks the list, sees they're already inside, and just rejects the duplicates at the door. So the final count, the length, isn't 5, it's only 3. Clean, simple, and unique. Okay, but here's where sets go from being a neat little container to something really powerful. It's not just about what they hold, it's about how they can interact with each other. This is where things get super interesting.
First on the list is the union. You can think of this as just uniting two sets. You're creating a brand new, bigger set that contains every single element from the first set plus every single element from the second set all rolled into one. And of course, that no duplicates rule still applies.
So let's use these two sets as our guinea pigs. We've got set 1 with 54, 19, and 75, and we've got set 2 with 75 and 12.
So what's their union going to look like? Well, you just dump everything from both sets into a new one. We get the 54, the 19, and the 12. And hey, notice the 75? Even though it was in both of the original sets, it only shows up once in the final result. That's the set doing all the hard work of handling duplicates for us automatically. Pretty cool, huh?
Next, we've got intersection. If union is all about combining everything, intersection is the exact opposite. It's all about finding the overlap, the common ground. It gives you a new set that contains only the elements that exist in both of the original sets. So, using our same two sets, what's the one and only thing they have in common? Yep, it's the number 75. That is the only element that's in both places. So, their intersection is just a tiny new set containing that one number. And by the way, this is literally how a social media app instantly shows you the friends you have in common with someone else. It's just a set intersection.
And finally for this group, we have difference. This one's a little tricky. It finds what's unique to the first set. It gives you back everything from set X that is not found in set Y. And for this one, you really have to pay attention because the order you do it in matters a lot. And here is the perfect proof of why that order is so critical. If we do set 1 minus set 2, we're basically asking, what's in the first set that isn't in the second one? And the answer is
54, and 19. But if we flip it around and ask, what's in set 2 that isn't in set 1, the only answer is 12. See? Two totally different results.
Okay, so we can combine and compare sets. That's awesome. But what if we want to transform the data inside a single set? Well, that's where two more super handy operations come into play: filter and map.
A filter does, well, exactly what it sounds like. It sifts through everything in the set and creates a new, smaller set, a subset, that contains only the elements that pass a specific test. In the programming world, this test is often called a predicate, but you can just think of it as a true or false question you ask about each item.
For example, let's say our test is this number even? We apply that question to every single element. Is 91 even? Nope. Is 12 even? Yep. 48? Yes. And so on. The filter then gives us a brand new set that contains only the things that pass the test: 12, 48, and 62.
Now, mapping is a little different. Instead of picking and choosing elements to keep, a map transforms every single element in the set by applying some kind of function to it. It creates a whole new set from the results.
For example, if we have this set of numbers and our mapping function is divide everything by 2, we just go through and do it. 18 becomes 9, 44 becomes 22, 38 becomes 19, and 6 becomes 3. And boom, you end up with a completely new set of transformed values.
So we've gone through a lot of abstract ideas and numbers. Why does any of this actually matter? Well, it turns out these simple rules are the building blocks for countless features that we all use every single day.
This table is a great little summary of that toolkit we've been exploring. And this isn't just theory from a textbook. These are basically the exact kinds of commands you'd find in programming languages, like Python, that are used to build the apps on your phone right now.
And really, that brings us to the final thought. Once you know what to look for, you start seeing sets hiding in plain sight. Every time you see a list of unique tags on a blog post, that's a set. And like we said, when your social media app shows you friends in common, that's just a set intersection. So I'll leave you with this question. Now that you know the rules of the game, where do you see sets at work in your digital life?